What if 3I Atlas proves more than an odd comet? What if it becomes a cosmic black swan, an event that forces a rewrite of core assumptions about gravity, time, and coincidence? Initial reports called it a routine interstellar visitor. It did not behave like one. Hit like and subscribe because you don't want to miss what happens next as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. Observers saw acceleration inconsistent with standard models. Brightness pulsed. Its orbit shifted in ways equations failed to predict. Telescopes across continents focused on the same anomaly. Data streams in control rooms showed patterns that did not match existing templates. The object shed water at nearly 3 astronomical units from the Sun, a distance where comets normally remain inert. Spectra from the James Webb Space Telescope revealed a coma dominated by carbon dioxide at an unprecedented ratio of roughly 8:1 versus water. Dust production, polarization of scattered light, and photometric behavior all sat at the edges of known distributions. The orbit is hyperbolic and retrograde, yet aligned closely with the ecliptic plane. Perihelion occurred on October 29, 2025. The object passed within 19 cents of Mars in early October, will pass near Venus in November, and will approach Jupiter in March 2026. Those close approaches do not present an impact threat today. They raise a different question: can tiny gravitational nudges produce large effects over decades? In chaotic orbital systems, small offsets grow with time. A millimeter per second change now can translate into kilometers of deviation decades later. Planetary defense networks do not track every small body with that time horizon in mind. Non-gravitational acceleration failed to match observed outgassing rates. One explanation requires a nucleus far denser or more massive than reflected brightness suggests. Another requires unknown internal structure or symmetric thrusting that cancels net motion. Each option breaks standard assumptions. The scientific community split along predictable lines. Many experts pressed caution and called for more data. Others urged broader investigation and archival searches. The media amplified both voices and framed the debate with dramatic imagery. Public reaction provided its own feedback loop. Speculation drove attention. Attention shifted funding priorities and telescope schedules. Social narratives influenced decisions that should remain purely empirical. To judge whether the event qualifies as a space black swan, use 3 simple criteria. First, unpredictability beyond current theoretical space. Second, high impact on scientific frameworks, infrastructure, or policy. Third, irreversible consequences or post-event explanations that appear obvious. By this test, 3I Atlas sits near the threshold. It does not meet every criterion now. It could cross the line if fragmentation, unexpected orbital perturbation, or a novel signal appears. 5 broad pathways link the object to large consequences. An orbital domino could nudge small bodies into risky trajectories over long intervals. A fragmentation event could produce components with anomalous motion. A coincident solar disruption could amplify infrastructure impacts. A brief structured emission buried in noise would pose interpretive and political dilemmas. Subtle ionospheric or telemetry anomalies could indicate unexpected interactions with local space environments. Each pathway ranges from plausible to speculative, but all hold asymmetric consequences if the improbable occurs. Fragmentation and orbital perturbation are the most grounded concerns. Comets fragment routinely under perihelion stress. If a fragment displays motion inconsistent with known ejection physics, the anomaly becomes a probe into internal structure or unknown forces. Small gravitational tugs on co-orbital populations, trojans, or marginally stable asteroids could seed risks that manifest decades from now. These scenarios demand long-term monitoring, not only immediate follow-up. More speculative ideas demand cross-disciplinary checks. Search radio archives for narrowband pulses during perihelion windows. Compare pulsar timing residuals, spacecraft telemetry timestamps, and ionospheric logs across observatories. Check fast radio burst catalogs for coincident events in the object's sky position. Any correlated pattern would not prove artificial origin. Correlation would justify deeper inquiry and force reassessment of filtering practices across observational pipelines. The event exposes system design limits. Observation systems operate in silos. Planetary defense tracks near-Earth rocks. SETI scans radio bands. Solar monitoring focuses on the Sun. Archives filter noise through models tuned for familiar signals. Those filters discard anomalies that fall outside expected templates. Artificial intelligence offers a corrective. Machine learning applied to archival data has uncovered exoplanets, irregular transits, and galaxy morphologies missed by classical pipelines. Anomaly detection frameworks trained without rigid priors could highlight features humans dismiss. AI will not replace judgment. It will flag anomalies for human evaluation. Robust discovery needs replication across instruments, independent algorithms, and open data sharing. Replication remains the safeguard against false positives and against premature claims that damage credibility. Even if 3i Atlas resolves into a natural but unusual object, the episode serves a lesson in humility. Interstellar visitors now exist as a detectable class. Their chemistry and dynamics expand the parameter space of small-body science. Instrument design, observation strategy, and archival practice require updates to avoid future missed signals. If the object becomes a true black swan, the scientific, cultural, and policy impacts will follow naturally from the evidence. If the object remains an outlier within existing models, the value lies in model refinement and improved readiness. The deeper implication concerns pattern recognition itself. The universe produces anomalies across scales, FRBs with strange repeat behaviors, trans-Neptunian objects with clustered orbits, tentative hints of variability in fundamental constants, timing residuals in pulsar arrays. Each anomaly could stand alone or belong to a broader signal we have not yet seen. The path from noise to discovery requires flexible data strategies and tools that preserve unexpected information rather than suppress it. 3i Atlas is fading into the outer system. Its physical window is closing. What matters now is the archival work, the coordinated analysis, and the willingness to treat low-probability, high-impact possibilities with methodical care. Monitor post-perihelion light curves, update non-gravitational acceleration models, search radio archives, reprocess telemetry, and compare ionospheric datasets. Each thread might reveal a pattern otherwise hidden. Either outcome yields progress. If the object proves routine, we extend models and improve detection protocols. If it proves extraordinary, we face a paradigm shift. Either result strengthens science if investigators remain transparent and thorough. You live under an open sky. That sky will continue to produce surprises. Our instruments, AI tools, and scientific norms must evolve so we notice anomalies and evaluate them properly. The next interstellar visitor is already on its way. When it arrives, your judgment about preparedness will matter. Did we see it coming, or did we look the other way? 3i Atlas might be the most studied speck of ice and dust in modern astronomy. Yet for all the data collected, its story remains open. The longer scientists look, the stranger it becomes. Every new measurement challenges a different assumption about how the universe behaves. At first glance, 3I Atlas was unremarkable, another interstellar body, catalogued and tracked, expected to obey the known physics of comets. But over weeks, the evidence began to contradict the models built to explain it. The object brightened far beyond predictions, then dimmed unpredictably. Spectroscopy revealed a coma dominated by carbon dioxide instead of water. The amount of gas released suggested enormous energy, yet the resulting motion was minimal. It was as if the jets were firing, but the object refused to move. Observers compared the phenomenon to a spacecraft burning fuel in perfect balance, thrusting in every direction and going nowhere. Each telescope that turned its sensors toward the comet added another layer of confusion. The James Webb Space Telescope recorded thermal emissions inconsistent with surface temperature models. The Nordic Optical Telescope found dust scattering patterns unseen in any other comet. Polarimetric data implied a surface texture too smooth or too metallic to fit expectations. No single observation was enough to call the object unnatural, but the collection of oddities pointed toward gaps in understanding. Comets are supposed to be simple. They are frozen debris, leftovers from planetary formation, bound by gravity and shaped by sunlight. Their behavior is predictable because their ingredients and dynamics are familiar. When one defies the template, every assumption is forced into question. Researchers debated whether 3I Atlas originated from a system with different chemistry, one richer in carbon dioxide ices, or whether it experienced some unknown interstellar process that altered its structure during its journey toward the Sun. The debate is more than academic. If 3I Atlas turns out to have a composition never seen before, it would redefine how scientists think about planet formation beyond the solar system. If its acceleration proves inconsistent with known physics, it could expose limits in the gravitational models used for everything from spacecraft navigation to orbital prediction. Each unanswered question branches into a web of implications. The public fascination grew in parallel with scientific tension. News outlets ran stories comparing the comet to Oumuamua, the 2017 object that inspired similar speculation. Commentators asked whether we were witnessing technology instead of geology. Social media amplified every theory, from artificial probes to hidden government monitoring. The effect was cumulative. Attention generated anxiety, and anxiety generated more attention. Scientists faced an uncomfortable reality: the narrative was escaping their control. Inside observatories, discussions became more practical. The community needed a framework for dealing with rare events that straddle the line between natural and unknown. A space Black Swan framework began to form. The idea was to classify anomalies not by probability but by consequence. If an event has a small chance of being catastrophic or revolutionary, it deserves investigation regardless of likelihood. The cost of false alarms is finite. The cost of missed discoveries is immeasurable. In practice, this philosophy demands new kinds of monitoring. Traditional comet observation campaigns track brightness, trajectory, and composition. Black Swan analysis adds additional layers: electromagnetic scans across radio and optical bands, magnetometer readings, solar wind coupling models, and archival searches for correlated signals across unrelated instruments. The goal is not to prove a single hypothesis but to detect patterns that ordinary science might overlook. The 3I Atlas project became a case study for this method. Teams at NASA, ESA, and several independent observatories shared data through the International Asteroid Warning Network. Machine learning algorithms combed through terabytes of images and spectra, searching for subtle trends in brightness and jet orientation. Ground-based radar arrays cross-checked orbital perturbations against small-body databases. None of the results were definitive, but each narrowed the field of possible explanations. While scientists debated the physics, philosophers and sociologists examined the reaction itself. They called it the psychological singularity, a term describing the point where collective curiosity transforms into a self-sustaining phenomenon. Historically, such moments have accompanied astronomical discoveries: Halley's Comet in 1910, the 1938 radio broadcast of the War of the Worlds, and even the 1997 discovery of potential Martian microfossils. Each case revealed how quickly public imagination can elevate an event beyond its empirical boundaries. The 3I Atlas case demonstrates that science and culture now operate in feedback. When speculation reaches a critical mass, institutions must respond, even if the science remains uncertain. Funding proposals appear overnight. Observation priorities shift. Political leaders request briefings. The comet becomes significant not for what it is, but for what it represents, the reminder that we are not in control of our cosmic neighborhood. Beyond the sociology lies a deeper scientific challenge. The solar system is not an isolated laboratory. It is a porous region influenced by galactic tides, dark matter density variations, and occasional visitors from interstellar space. Each object that enters it is a messenger from elsewhere. 3I Atlas is only the third confirmed interstellar object, after Oumuamua and Borisov. Statistically, hundreds more should pass through every decade, though most will remain undetected. As survey telescopes such as the Vera Rubin Observatory begin operations, detection rates will climb sharply. Scientists must decide how to treat these visitors, as curiosities or as potential catalysts for new physics. Some researchers propose permanent interstellar object watchlists. These would integrate radar, spectroscopy, and radio monitoring under a unified framework. Each new object would be catalogued for long-term tracking, its data shared across agencies. Artificial intelligence would play a central role, scanning for deviations from expected models. This approach mirrors the evolution of planetary defense systems, built not because impacts are frequent, but because the stakes are high. The AI element introduces both promise and risk. Algorithms excel at detecting patterns but lack understanding. When trained on existing data, they reproduce human biases. To avoid this, scientists are designing unsupervised models that look for the unexpected. These systems are fed raw data without human labels. They flag outliers, events, spectra, or time series that differ statistically from the rest. One prototype at Caltech recently rediscovered several known comets by anomaly detection alone and identified 3 additional objects previously ignored as noise. None turned out to be artificial, but the method proved that novelty can be found where no one is looking. Applying similar algorithms to the 3I Atlas dataset might reveal overlooked structures. For example, a repeating 6-hour brightness cycle could suggest rotation or dual-core behavior. A correlation between outgassing direction and non-gravitational acceleration might hint at internal asymmetry. An unusual synchronization between brightness and solar wind conditions could imply magnetic coupling. Each possibility leads to new models and new tests. Beyond the comet itself, the episode exposes a deeper truth about modern science. Data volume now exceeds human attention. Every night, telescopes produce more information than the global research community can analyze. Automated pipelines filter out noise to keep workflows manageable. Yet among those discarded pixels may lie the next paradigm shift. The risk is not ignorance but overconfidence in automation. The future of astronomy will depend on building systems that remain open to the improbable. 3I Atlas also connects indirectly to other anomalies across disciplines. Fast radio bursts show patterns that standard magnetar models fail to explain. Extreme trans-Neptunian objects display orbital clustering that hints at an unseen planet or statistical bias. Pulsar timing arrays reveal residuals that do not fit gravitational wave models. Even measurements of the fine structure constant show faint hints of variability across cosmic time. Each case alone can be written off as noise. Together, they suggest the possibility that our universe operates with more variability than current physics allows. If the fine structure constant truly varies, electromagnetic interactions change slightly across time and space. If spacetime itself fluctuates at small scales, atomic clocks may desynchronize subtly, and pulses from distant neutron stars may arrive earlier or later than predicted. A cluster of such anomalies during 3I Atlas's perihelion would raise questions far beyond cometary science. It would imply that local space is not uniform, that physical constants may differ in small regions of the galaxy, and that our instruments, tuned to stability, might be blind to small-scale chaos. This line of thought leads to the most speculative but philosophically rich hypothesis: perhaps 3I Atlas did not cause anomalies but revealed them. Its trajectory through the inner solar system served as a probe through regions of varying gravitational or electromagnetic conditions. If true, the comet becomes a diagnostic tool, exposing flaws in our models rather than in itself. Scientists would need to compare every measurement, light curves, radar reflections, trajectory residuals against environmental variables such as solar wind density, interplanetary magnetic field strength, and cosmic ray flux. In the long view, the comet becomes less an object of mystery and more a mirror reflecting the limitations of our methods. Every discrepancy forces refinement. Every unanswered question highlights how fragile our sense of certainty remains. From a practical standpoint, the lessons are clear. First, observation programs must treat interstellar visitors as multi-domain events. Optical, infrared, radio, and magnetometric data should be collected simultaneously. Second, archival data needs constant reanalysis as new tools become available. An anomaly dismissed in 2025 might become significant in 2030 when algorithms or calibration improve. Third, public communication strategies must balance curiosity with precision. Speculation should invite exploration, not hysteria. The line between transparency and sensationalism is thin but essential. The broader context includes planetary defense and long-term risk management. Interstellar objects, though rare, can pass close to planets and asteroids, subtly altering trajectories. The cumulative effect of such encounters over centuries could reshape the distribution of near-Earth objects. Planetary defense planning has focused on known bodies within the solar system. The 3I Atlas event suggests that external perturbations should enter those calculations. In the social realm, 3I Atlas reveals how science functions as both knowledge and narrative. The same data that drives research also fuels collective imagination. When the unknown enters the public sphere, it becomes a story about meaning, not measurement. The question of whether something is natural or artificial becomes secondary to what that possibility represents. Fear and hope both find room inside the same observation. The lasting importance of 3I Atlas may have little to do with its chemistry or motion. Its true value lies in what it exposed, the interplay between data, interpretation, and belief. It showed how quickly certainty dissolves under anomaly, how institutions struggle with ambiguity, and how the public turns mystery into mythology. It forced scientists to confront not only the limits of physics but the sociology of discovery itself. By early 2026, the comet will be a faint speck receding into interstellar space. Its light will fade below the reach of telescopes. But the data will remain, archived across observatories, waiting for re-examination by future tools. Perhaps decades from now, a graduate student running a new algorithm will find a small residual, a pattern invisible today, and the story will reopen. Whether the conclusion points to new physics or human error, the lesson will be the same: the universe is larger, stranger, and less predictable than any model can contain. Science advances not by certainty but by confrontation with surprise. 3I Atlas delivered that surprise in abundance. It reminded researchers that models are maps, not territory. It reminded the public that space is not empty but alive with motion and anomaly. It reminded everyone that vigilance is the price of understanding. Somewhere beyond Neptune, another object is already on its way toward the Sun. When it arrives, the systems we build now will determine how well we respond. Whether it behaves predictably or breaks the rules again, the task will be the same: observe without assumption, question without panic, and record everything. Because every once in a while, the sky stops following the script, and in those moments the universe hands us its next lesson. The 3I Atlas encounter may not change physics. It might change how we look for what physics misses. It might mark the beginning of a new observational philosophy, one that treats anomalies not as nuisances but as invitations. And if that becomes its legacy, then this frozen traveler from another star will have done its work. 3I Atlas has now become more than an astronomical curiosity. It has evolved into a mirror for how humanity deals with the unknown. Its story threads across science, media, psychology, and philosophy, showing how fragile the boundary is between explanation and imagination. As it moves farther from the Sun, its brightness fading to invisibility, the arguments it provoked still expand outward like ripples on water long after the stone has sunk. For scientists, the comet forced an uncomfortable realization: the universe remains more complex than the models built to contain it. Every generation assumes its frameworks are complete until reality exposes the gaps. 3I Atlas is that gap: an object behaving according to rules no one fully understands. Its carbon dioxide dominance, non-standard acceleration, and strange polarization data together signal either an unrecognized natural process or an error in how we define natural itself. Researchers began to catalog each anomaly methodically. The composition problem led to new hypotheses about interstellar chemistry. One group suggested that 3I Atlas formed in a region rich in carbon-bearing volatiles, perhaps closer to a red dwarf star where co-ices condense earlier than water. Another proposed that cosmic radiation in interstellar space had restructured the outer layers, sealing water ice beneath a crust that vented first when warmed. Both ideas are testable, both demand revisions to existing comet models, and neither fully fits the data. The motion problem is harder. When a comet vents gas, the recoil from the jets changes its path slightly. The amount of deviation can be predicted from the outgassing rate. In 3I Atlas, the deviation was too small. Either the jets were perfectly balanced, which nature seldom achieves, or the nucleus was far denser than expected. Density implies composition, and composition implies origin. If the nucleus is rock metal rather than porous ice, it must have formed under higher pressures, perhaps inside a planetesimal rather than in a disk of dust. That alone would make it unique among known comets. Some observers speculated that the symmetry of its jets might arise from internal cavities arranged along axes of rotation, creating near-perfect thrust cancellation. Others argued that the nucleus might not be a single body at all, but a cluster of fragments orbiting a common center of mass, behaving as one. If true, its stability would challenge existing models of cohesion for loosely bound aggregates. Whatever the case, the object seems to obey its own physics. And in science, when something behaves as if new laws apply, those laws must be investigated, even if the outcome is mundane. The orbital geometry adds another layer. Interstellar objects should arrive from random directions, yet 3I Atlas came in almost coplanar with the planets. Statistically, the odds are tiny. Either coincidence misleads us, or something about the solar system's gravitational architecture channels such trajectories into the ecliptic. A few dynamicists proposed that the galaxy's disk may preferentially focus interstellar debris along certain inclinations, meaning the object's alignment might be less remarkable than it appears. But the near-perfect match still disturbs the pattern-seeking mind. When the comet passed Mars, sensors on orbiters detected no direct interaction. Yet the geometry of the encounter invited new simulations about long-term perturbations. The question became whether interstellar objects, passing periodically through the inner solar system, could gradually modify asteroid orbits in ways that accumulate over millennia. Models show that even a minute gravitational pull, repeated across eons, can alter the architecture of small body populations. If so, every visitor like 3I Atlas contributes to an invisible sculpting of the solar system, a slow, statistical shaping that might explain certain orbital clusters. In this view, black swans in space are not rare shocks but steady background forces we have yet to notice. Parallel to the scientific analysis came a wave of technological adaptation. Observatories restructured their data pipelines to retain more raw information. Previously, most telescopes compressed or filtered data in real time to save bandwidth. That practice discards low-signal anomalies. Now, after 3I Atlas, several agencies began archiving full-resolution feeds. The change consumes massive storage, but it ensures future reanalysis when computing power and algorithms improve. It is an expensive hedge against ignorance. Machine learning teams began to train neural networks not only to identify known patterns but to recognize statistical strangeness itself. The algorithms learn what normal looks like, then flag deviations even if they correspond to no known category. Early tests uncovered calibration errors, cosmic ray hits, and a few genuine discoveries: minor asteroids, variable stars, and one short-lived flare that had been dismissed as noise. The process confirmed that novelty detection works. Applied at scale, it might catch the next 3I Atlas before it drifts away. Philosophers of science saw in this shift an epistemological revolution. Traditional inquiry starts with a hypothesis. The new approach begins with anomaly detection, hypothesis second. AI does not need belief, it needs contrast. It tells us where our expectations fail. Humans then decide whether failure means discovery or error. The partnership mirrors the larger dynamic between reason and wonder that defines science itself. While scientists looked upward, psychologists and sociologists examined the human reaction below. Why does an icy rock millions of kilometers away evoke such intensity? The answer lies in how humans relate to uncertainty. The modern world depends on predictability, on models that claim to foresee risk. A true anomaly undermines that comfort. The idea of a cosmic event beyond prediction triggers both fascination and fear, the same emotions that accompany economic crashes or pandemics. Black Swan is as much a psychological concept as a physical one. Media ecosystems amplify that effect. In the age of instant communication, speculation spreads faster than data. Within hours of the first reports, social platforms were full of claims about alien probes, secret monitoring, and government silence. Each claim fed engagement algorithms that reward emotion over accuracy. Scientists who tried to correct the record found themselves drowned in noise. The comet became a cultural event before it became a scientific one. Institutions learned from that chaos. Space agencies now draft communication protocols for anomalous detections. The goal is not censorship but coherence, to present uncertainty without fueling hysteria. The challenge is linguistic. Words like mystery and unexplained attract attention but distort perception. The preferred phrasing, data inconsistent with model predictions, conveys less drama but more truth. Still, humans crave stories, and the line between story and science remains porous. Amid this, another field found relevance: risk management. Analysts borrowed methods from finance to quantify scientific uncertainty. They modeled 3I Atlas as a stochastic variable within a system of incomplete knowledge. The resulting charts resemble those used to price rare disasters. In both domains, low probability, high-impact events dominate long-term outcomes. The conclusion is pragmatic: allocate resources not by likelihood but by potential consequence. The principle that governs insurance portfolios now applies to interstellar comets. Beyond the Earthbound debates, the comet's journey continues. After perihelion, its brightness curve began to decline. Observers measured changes in tail length and composition. The ratio of Co to HO slowly dropped, suggesting surface depletion of volatile carbon compounds. That evolution hints that 3I Atlas might not be a single-stage object but a layered structure, each layer exposing a different chemistry as it erodes. If confirmed, this would support models where interstellar ices form under variable radiation environments, recording the history of their parent systems like cosmic fossils. High-resolution imagery also revealed a complex coma morphology, jets emanating in spirals rather than fans. That pattern indicates rotation combined with uneven venting, perhaps from fissures aligned along specific axes. Using light curve periodicity, teams estimated a rotation period near 6 hours, though secondary modulations suggest a tumbling motion. Tumbling would explain the inconsistent acceleration, forces averaging out over irregular spin cycles. The data is incomplete, but the picture grows clearer: an object both familiar and foreign, natural yet strangely disciplined. While observational work continued, a quieter revolution unfolded in the archives. Groups re-examined past anomalies once dismissed as noise: brief radio bursts, timing offsets, unexplained spectral lines. Some matched the dates of the comet's perihelion window. None provided definitive proof of correlation, but the coincidence reignited interest in the possibility of transient signals, short, structured emissions too weak or brief to classify. The discussion returned to the same unresolved question: if a non-repeating signal appeared once and never again, would we recognize it before it was gone? The search for such signals connects 3I Atlas to broader astrophysical mysteries. Fast radio bursts, repeating irregularly across galaxies, show polarization and dispersion patterns that challenge existing magnetar models. Their origins remain unclear. Some physicists entertain the idea that FRBs might not all be extragalactic. A subset could arise from nearby sources we misinterpret because of data filters tuned for distant events. If true, local transients might be common yet unseen. Cross-referencing FRB catalogs with known comet passages becomes a new frontier of research. Farther out, the discovery of extreme trans-Neptunian objects adds weight to the possibility that unseen masses influence outer solar system dynamics. The hypothetical Planet 9 remains unobserved, yet statistical clustering of orbital elements persists. Each new data point either strengthens or weakens the case. The conversation around 3I Atlas feeds into that debate by reminding scientists how easily observation bias masquerades as pattern. Sometimes alignment means cause, sometimes it means coincidence amplified by attention. Quantum physics enters the story indirectly. Recent measurements hint that the fine structure constant, the number defining electromagnetic strength, might vary slightly across the universe. If true, physical laws differ minutely from place to place. In such a universe, local anomalies like 3I Atlas are not violations but reflections of variability. The same may apply to time itself. Pulsar timing arrays record microsecond residuals unexplained by gravitational waves alone. Some attribute them to instrument drift, others to the underlying fabric of space fluctuating unpredictably. If time and constants are not perfectly stable, then every precise prediction rests on shifting ground. The comet may be our first visible reminder of that instability. AI will soon become essential for navigating these complexities. Next-generation telescopes such as the Vera Rubin Observatory and space missions like the Nancy Roman Telescope will produce tens of terabytes of data daily. Human analysts cannot review it manually. Automated systems will decide what is interesting. The danger is that algorithms trained on existing expectations will discard true novelties. To counter this, scientists are developing curiosity-driven systems, models that reward the detection of statistical surprises rather than conformity. The philosophy mirrors the lesson of 3i Atlas: look for what does not fit. Economically, the case has spurred discussion of astrorisk, the quantification of potential disruptions from celestial events. Insurers and infrastructure planners already assess solar flare risk. Now some propose extending models to include unknown classes of cosmic phenomena. The objective is not to predict every anomaly but to design systems resilient to surprise. In this sense, 3i Atlas serves as a rehearsal for future crises, scientific or otherwise. Culturally, the comet has entered art, literature, and film. Artists portray it as a symbol of the unknowable, something that defies both awe and explanation. Documentaries trace its discovery as a metaphor for human curiosity. Writers use it to question faith in technology. The object has transcended astronomy. It has become narrative fuel, proof that even in an age of precision instruments, mystery endures. For educators, it provides a case study in scientific method under uncertainty. Classrooms now analyze the event to teach critical thinking, how to separate data from interpretation, how to handle incomplete evidence, and how to communicate ambiguity responsibly. Students learn that science does not remove mystery, it manages it. By late 2026, the comet will have receded beyond Jupiter's orbit. Observations will become sporadic. Yet the data already gathered will occupy researchers for years. Each reanalysis may yield new insights, each insight another reminder of how much remains unknown. Whether 3i Atlas ultimately proves ordinary or extraordinary is almost irrelevant. Its true legacy lies in how it reshaped inquiry itself. The object forced a shift from closed certainty to open vigilance. It united astronomers, data scientists, philosophers, and the public in a shared exercise of curiosity. It reminded everyone that black swans are not failures of prediction but reminders that reality resists compression into equations. The universe continues to behave independently of expectation. The final lesson is humility. Science is the art of being wrong gracefully, of revising models without surrendering to confusion. 3i Atlas delivered that discipline. It showed that even with our telescopes, satellites, and algorithms, the cosmos still surprises. The next anomaly may come tomorrow or a century from now. Preparedness means maintaining systems flexible enough to detect it and minds willing to accept it. Somewhere beyond the range of current sensors, another object already moves toward the Sun. It may be inert, it may be transformative. Whether we recognize it depends on what we learned from this one. When it arrives, telescopes will turn, data will pour in, algorithms will hum, and humanity will once again face its oldest question. What, exactly, are we looking at, and do we understand what it means? 3i Atlas is gone from sight, but the questions it left behind are still multiplying. The comet's faint trajectory through the outer solar system is now a faint line of data points. Yet on Earth, its impact deepens. Every field it touched, astronomy, computation, risk analysis, even philosophy, has begun to reorganize around its shadow. For planetary scientists, the lesson is methodological. Observation networks were never built for interstellar visitors. Tracking software assumes bound orbits. Spectroscopic libraries assume compositions derived from solar system chemistry. Calibration routines presume known ranges of brightness and temperature. 3i Atlas broke each of those assumptions. In response, laboratories are now rebuilding their toolchains. Orbit solvers are being rewritten to handle hyperbolic trajectories natively. Chemical models are expanding to include exotic ices predicted for exoplanetary disks. Detector pipelines are being modified to flag values once auto-discarded as out of range. The object forced an upgrade of the planetary science infrastructure without waiting for permission. Data policy is changing as well. Agencies once guarded raw observations behind institutional walls. Since the 3i Atlas campaign, more observatories have adopted real-time public releases. The reason is pragmatic: distributed eyes catch mistakes faster. During the 2025 perihelion phase, several anomalies were corrected only after independent amateurs noticed inconsistencies in timing metadata. Crowdsourced verification became a de facto safeguard against systemic bias. Now, community peer review during live observation runs is becoming normal. The boundary between professional and citizen science continues to blur. At the same time, a quiet intellectual migration has begun. Researchers trained in economics, complex systems, and catastrophe modeling are joining planetary defense teams. They bring probabilistic thinking shaped by financial tail risk analysis, the same logic that guides insurance portfolios. In those models, rarity is no refuge. A once-in-10,000 event deserves attention when its cost is existential. Applied to astronomy, this mindset turns Black Swan vigilance into policy. Missions are now designed with contingency protocols for unmodeled behavior, adaptive exposure schedules, flexible sensor arrays, and redundant communication channels able to capture data even when parameters drift beyond design limits. The cultural layer follows close behind. Museums and science centers have turned the Comet into an educational touchstone for uncertainty. Exhibits pair raw data with competing interpretations, inviting visitors to judge plausibility themselves. Teachers use the case to explain the difference between anomaly and error, correlation and causation. Philosophy departments treat it as a living example of epistemic humility, the acceptance that truth often hides in noise. Technology companies have seized on the metaphor. Atlas protocols now describe AI systems that audit their own blind spots. These frameworks deliberately introduce randomness into training data to expose brittle assumptions. The approach began in astronomy but is spreading to medicine and climate modeling. The principle is simple: anything that never surprises itself is already obsolete. In the policy sphere, the event revived dormant discussions about scientific preparedness. Governments accustomed to budgeting for weather satellites and planetary missions now face a broader question: how do you budget for the unknown? Some agencies propose a standing anomaly fund, a rapid response pool allowing telescopes to redirect time instantly when unexplained phenomena appear. The idea borrows from disaster relief mechanisms, money held in reserve not for what is likely, but for what will matter. Economists studying innovation note that such funds mirror venture capital. Small investments spread across high-risk prospects yield disproportionate returns. In science, the same logic applies. One anomaly correctly pursued can redefine decades of theory. 3i Atlas demonstrated that the cost of curiosity is minimal compared to the cost of complacency. Philosophically, the Comet resurrected an old argument: is nature truly random, or do patterns hide beneath apparent chaos? For centuries, humans oscillated between these poles. 3i Atlas sits precisely in the middle. It behaved chaotically but within measurable boundaries. Its deviations were small enough to debate, large enough to unsettle. It showed that the universe need not break laws to surprise us, it only needs to expose where those laws stop working cleanly. Within research institutions, a more technical revolution brews. Machine learning now handles data triage, but its success breeds dependence. The next step is interpretability, training systems not only to flag anomalies but to explain why they look anomalous. Astronomers demand causal insight, not just correlation maps. Developers respond with hybrid models that merge physical equations with neural architectures. The resulting physics-informed AI represents a new class of scientific instrument, one that learns without discarding theory. 3I Atlas was the stress test that made such innovation urgent. Meanwhile, sociologists track how the Comet's narrative continues to evolve online. Interest has not faded, it has matured. Discussion forums that once argued about aliens now analyze orbital mechanics. Amateur programmers write scripts to replicate brightness curves. The event has turned a fragment of rock into a long-term public laboratory for critical thinking. In academic circles, new conferences have emerged under titles like Anomalies and the Architecture of Science and the Epistemology of Surprise. Papers explore how to formalize the study of outliers, how to make a discipline of exception rather than routine. One recurring theme is methodological pluralism, the idea that no single model should monopolize interpretation when evidence remains ambiguous. 3I Atlas provides the test case for that principle in action. The Comet also triggered introspection about communication between disciplines. During the peak of the 2025 analysis rush, astrophysicists, statisticians, and AI researchers often worked in isolation, duplicating effort and misinterpreting one another's outputs. Post-event audits revealed that more integrated workflows would have resolved several disputes early. The solution now taking shape is the Observation Consortium, a permanent cross-domain task force prepared to respond collectively to any new interstellar detection. The model borrows from epidemiology, rapid data sharing, standard protocols, and global coordination. Beyond institutional change, a quieter emotional current runs through the scientific community: relief. The Comet reminded professionals why they entered the field. After years of routine survey work, here was mystery again, something that refused to fit. Many admit that their best ideas were born not from answers but from confusion. 3I Atlas gave them that confusion in abundance. From a cosmic perspective, the event may mark the beginning of an age of continuous vigilance. Interstellar objects are likely common, detection rates will rise as sensors improve. Each one is a sample of another star system, a natural probe crossing the gulf between suns. Studying them turns astronomy from distant observation into direct sampling of galactic diversity. Some scientists now advocate permanent interstellar interception missions, small spacecraft placed on standby to pursue any inbound object. These interceptors would launch within weeks, gather in situ data, and transmit before the object escapes again. The proposal's feasibility improved after Atlas, the political will followed soon after. The next frontier lies in synthesis. Data from comets, asteroids, pulsars, and quantum experiments once occupied separate silos. Now, correlation platforms seek links across them. When timing anomalies align with interstellar passages or solar cycles, patterns emerge that neither field could see alone. Whether those patterns reveal new physics or coincidence remains unknown, but the process itself expands the horizon of inquiry. Ethicists have joined the conversation too. If AI systems detect signals that humans cannot interpret, who decides what counts as evidence? If pattern recognition blurs the line between natural and artificial, what responsibilities follow? The questions are no longer speculative. Algorithms already flag events beyond human comprehension. The Black Swan framework now includes ethical oversight. Every anomaly must be examined not only for scientific merit but for societal consequence. Through all of this, the public fascination persists because the story embodies a simple paradox. We know more about the universe than any generation before, yet we are reminded daily of how much we still miss. 3I Atlas exposed that tension. It was neither miracle nor threat, it was a messenger delivering humility. As of 2027, the comet drifts toward interstellar darkness. It will not return. But the systems built to understand it will remain. The new orbital models, AI detectors, data-sharing networks, and interdisciplinary frameworks will outlive their cause. In that sense, 3I Atlas achieved what every scientific anomaly should: it forced progress. And so the era that began with one wandering fragment of ice now continues without it. Each night, telescopes across the world collect torrents of photons, algorithms sift through petabytes of noise, and somewhere in that noise another anomaly waits. When it appears, an object, a signal, a shift in constants, the lessons of Atlas will guide the response. Record everything, assume nothing, stay curious. Because in the end, the Black Swan is not the comet. It is our own certainty. The story of 3I Atlas now exists between data and myth. The comet itself has gone silent, its last reflected sunlight scattered across the detectors of a few deep space observatories before fading into the noise floor. No new images arrive. No more light curves update. It is gone, swallowed by distance. What remains is the wake it left in human systems, algorithms rewritten, instruments recalibrated, and a sharpened awareness that certainty is temporary. When the object was first catalogued, most of the scientific world saw it as another entry in the expanding registry of interstellar debris. Routine, measurable, disposable. Yet in the months that followed, that simplicity evaporated. Every instrument that looked at it found something fractionally wrong. Each discrepancy alone was small, too minor to publish, too uncertain to explain, but together they built a cumulative tension. Outgassing inconsistent with temperature. Acceleration not matching mass. Chemistry out of equilibrium. A rotation period that shifted without obvious cause. None of these findings proved anything extraordinary. Together they refused to close the case. That refusal became the real event. For the first time in years, global science agreed not on an answer but on a question. Instead of proof, there was persistence. Observatories kept measuring long after formal campaigns ended. Students wrote theses on its anomalies. Analysts trained machine learning systems to test thousands of variations of orbital models. Governments quietly funded deeper surveys of interstellar space, not because they feared the comet, but because they feared what they had overlooked. 3I Atlas had become the teacher, and the lesson was unfinished. Across cultures, the comet acquired symbolic weight. In art, it represented perspective, the reminder that the universe does not require our comprehension. In literature, it became metaphor for transient knowledge, a thing glimpsed once and never again. The object's trajectory across the solar system traced a geometry of humility. It entered without announcement, disrupted models, absorbed attention, and then left. Its passage compressed the entire rhythm of science: observation, confusion, revision, acceptance. Yet beneath the symbolism remains the hard data. Thousands of spectra, terabytes of telemetry, radio flux logs, polarization maps, radar echoes, photometric time series, all stored, tagged, and waiting. The next decade of analysis will not seek drama, it will look for consistency. Researchers will test whether subtle fluctuations in co-ratios correspond to rotation phases, whether brightness decay matches models of delayed sublimation, whether minor deviations in orbital residuals correlate with known gravitational perturbations. The mystery may dissolve into ordinary explanations: crustal heterogeneity, vent shielding, measurement bias. Or it may not. Either result will carry equal value. Understanding is built from both discovery and elimination. The larger shift, though, lies not in any single finding but in process. The event accelerated the integration of human and machine observation. Before Atlas, AI-assisted astronomy by sorting data for known phenomena. After Atlas, it was reprogrammed to detect the unknown. Systems once designed to filter out anomalies are now tuned to preserve them. The pipeline of science has inverted. What was once noise now earns attention. That inversion may be the comet's most lasting legacy. It changed how knowledge organizes itself. Ethically, the experience also redefined responsibility. The comet story showed that withholding uncertainty can be as dangerous as exaggerating it. Public communication learned new discipline. Scientists learned that humility is compatible with confidence. To say we don't know yet became a mark of rigor, not weakness. The cultural reward for doubt grew stronger. Atlas forced transparency not through fear but through curiosity. Philosophers compare this to earlier moments when observation outpaced understanding: the first telescopic view of Jupiter's moons, the spectral discovery of dark lines in sunlight, the detection of cosmic expansion. Each event expanded scale and shrank certainty. 3I Atlas fits within that lineage, a small object revealing large ignorance. It reaffirmed that science is not a march toward closure but a sustained negotiation with complexity. In universities, new curricula now include modules on Black Swan methodology. Students learn statistical vigilance, model fragility, and cognitive bias in real case studies drawn from the Atlas data. Engineers design telescopes with wider dynamic ranges and error-tolerant software. Sociologists study how information flowed across networks during the 2025 observation window, tracing how rumor evolved into knowledge. Economists adapt the lessons to systemic risk management, treating the cosmos as another domain of uncertainty. For individuals, the comet's passage became a reminder of scale. A fragment of matter smaller than a mountain traveled for millions of years, crossed interstellar space, brushed the edge of a single star system, and vanished again. Humanity, equipped with detectors orbiting Earth, managed to notice. That fact alone proves something profound: our awareness now extends beyond the reach of our ancestors' imagination. Yet the awareness comes with a cost: recognition of how much still lies beyond view. By 2027, as its path carries it past the orbit of Jupiter and into darkness, no telescope can track it. Only predictive coordinates remain, mathematical ghosts of motion. But the influence continues. Funding proposals reference it as justification for new missions. Philosophical essays cite it as evidence that the frontier of knowledge lies not in expansion but in refinement. Even the language of everyday conversation absorbs its echo, Atlas as shorthand for the unexpected, for the event that changes the conversation without offering closure. Eventually, another visitor will come. Another object will appear at the edge of our sky, and once again sensors will turn and algorithms will search. Whether that object behaves normally or not, the tools built in response to 3I Atlas will be ready. We will record more data, preserve more anomalies, and question assumptions earlier. The next Black Swan, if it arrives, will not find us blind. So the comet leaves, and we remain. Every clean dataset invites a second look. Because 3I Atlas was never only a comet. It was a demonstration that the unknown still exists and that we are still capable of recognizing it. And that, more than any discovery, is the rarest event of all.